In the first lecture, we looked at Jacobi method, we looked at Gauss-Seidel method, both indirect methods. So how we calculate the solution is we iterate until we got some form of convergence. And we saw that the Gauss-Seidel method was quicker than the Jacobi method. Wouldn't it be nice if we can actually come up with some form of analysis which will tell us which method would be quicker? And good news is we can do that. And this uses the idea of the iteration matrix. So that matrix T, which I calculated for both Jacobi and Gauss-Seidel methods, I did say it's not that not very useful for actually calculating solutions. What it does do, it allows us to do some analysis. Okay, so here we have a theorem. Okay, if we have a sequence of solutions, so x to the superscript k, so this is just a sequence of solution vectors. And this, so our next sort of estimate of the solution is the iteration matrix T times a previous estimate of the solution plus some vector C. In this analysis, C is just ignored. Okay, it is there, but it doesn't really give us much information. Essentially, what we have here is a theorem that an indirect method will converge if the norm of the iteration matrix T is less than 1. So this is a requirement. If this norm of T is greater than 1, our method is not going to converge. Okay, so that's the key thing to understand. Okay, and unusually for me, I'm going to just present a proof of this. Okay, the proof is as follows. What we're going to do is we're going to define a vector E, which is the errors for a current estimation. And the errors, that vector E, will also follow T times the error from the previous estimation. Okay, so if we have a solution, we get the next solution by multiplying by T. The same will apply to the errors. Okay, well, so the EK is simply xk minus x, where x is the exact solution. So the error at the kth iteration is equal to the error at the k minus 1 iteration, but multiplied by T. Now, if we extend that logic further, that is equal to the error at the k minus 2 iteration multiplied by T. Okay, so in other words, T squared, so T is a matrix, multiplied by the error at the k minus 2 iteration. And we can keep going. So we could have T cubed is equal to the error at the k minus 3 iteration. So if we keep going all the way until we get back to the initial error, E0, we have T raised to the power k. Now this is a power. Okay, so that is T raised to the power k. Now recall that from matrix norms, okay, the norm of a product is less than or equal to a product of the norms. So if that's the case, okay, so applying this to EK equals T to the power k times our initial error, okay, so we can see that this norm here is going to be less than or equal to the norm of T raised to the power k multiplied by the norm of E. Now, if norm T is greater than greater than 1, that number raised to the power k is going to be greater than 1. It's going to go to infinity. If T is less than 1, that number, norm of T is less than 1, that number raised to the power k is going to go 10 to 0. So therefore, if the norm of T is less than 1, as k tends to infinity, our errors tend to 0. So if we were to keep iterating for an infinite number of times, eventually we'll get the exact solution. Okay, so that's the proof. So in short, we require that our iteration matrix have a norm of less than 1. Okay, that's not the only thing we could do with iteration matrices. We can actually tell or compare which method will converge faster. So if we calculate the norm of t, that will tell us whether a method will converge. We can actually tell which method will converge fastest. Okay, and this is using eigenvectors. Well, eigenvalues actually, not really eigenvectors. Oh, bit both. Okay, so recall from previous studies in the subject. This is a definition of an eigenvector. Okay, so any vector x is an eigenvector if the square matrix A times x is equal to lambda, which is some scalar, times x. Okay, lambda is known as an eigenvalue. And the eigenvalues of a matrix satisfies this equation. The A minus lambda times the identity matrix, calculate the determinant. Those values of lambda for which the determinant is equal to 0 is an eigenvalue. I'm not interested in how you calculate eigenvalues in this unit. You've done this in first and second year. So what I want you to use is simply Eig of A. Okay, that's all you need to use. Okay, you don't have to show me that you know how to calculate them. We've already done that in first and second year. Okay, this might be something new. The idea of a spectral radius. Okay, this is a rather posh name given to something which is quite simple. Spectral radius is simply the largest absolute eigenvalue of a matrix. So, okay, so this is a definition. This here is a Greek letter rho. So rho of A is equal to the maximum absolute eigenvalue of A. Okay, and there's a property of spectral radiuses or radii that spectral radii will always be less than or equal the norm of that matrix. So if you want to use MATLAB to calculate the spectral radius, okay, quite simply, Eigen will give you the eigenvalues, absolute will give you the absolute values, and then you find the maximum. That's all you do. So the spectral radius is the maximum absolute eigenvalues of a matrix. Okay. I'm going to tie all this together in a minute, so don't worry too much about that. Okay, so what I want is some kind of measure of how quickly an indirect method will converge. Okay, so consider your errors. Okay, we have our errors, which will grow or shrink. Hopefully, they'll shrink by this iteration matrix T. So if we calculate T minus the errors at the previous estimate, that will give us the errors at the current estimate. Or let's say T has n independent eigenvectors, and I've called them V in this case. So V is just some eigenvector of T. And corresponding eigenvalues lambda. Okay, remember that T times V, if V is an eigenvector, is equal to lambda times V. That's the definition of eigenvectors. Okay, so to start with, we have some linear combination of eigenvectors. So alpha is just some scalar. Doesn't matter what it is. It's some linear combination. Okay, that's at the initial error. The error at the first iteration will multiply the vector v by your iteration matrix T. Okay, so we'll have this expression. So some linear combination of alpha times your iteration matrix times your eigenvectors. Okay, well, from the definition of an eigenvector, if TV equals lambda v, I just replace TV here with lambda v there. Haven't changed anything, just the property of eigenvectors. Okay, that's the first iteration. What about the next iteration? Well, I multiplied v by t. Okay, so again, using this property up here, okay, if I replace the t with lambda, I'll have lambda I times lambda I, which gives me lambda I squared. So if I was to carry on for k iterations, I have this linear combination. So some number alpha, doesn't matter what it is, we don't care. your eigenvalues raised to the power k times your eigenvectors v. In a minute, we're going to totally get rid of the eigenvector, so don't worry about that. Okay, you don't need to calculate the eigenvectors, you only need the eigenvalues. Okay, so this means after k iterations, we can represent our error as a linear combination of lambda to the power k times the eigenvectors of t. Now, what I'm going to do here is I'm going to say, well, what if your lambda 1 is bigger than all other eigenvalues? So in other words, what if lambda 1 is your spectral radius? Okay, well, if that's the case, instead of this summation, so I've got a summation here that goes from I equals 1 to n. Okay, all I've done is I'm going to say I equals 2 to n. So I'm going to take out one of those terms out of that summation. So you can see here, I've taken out the first term out of the summation. Well, both of these terms, well, actually all terms here have a common, well, I can take out a common factor of lambda 1 to the power k. Okay, so if I factorize this by lambda 1 to the power k, I just get alpha 1 times the eigenvector, the first eigenvector, plus the summation. And in order to factorize this term, I have to divide by the lambda 1. Okay, so you can see all I've done there is I've taken out lambda 1 to the power k outside. Okay, well, if lambda 1 was the largest eigenvalue, all other eigenvalues divided by lambda 1 to the power k is going to tend to 0, because this number here is going to be less than 1. Any number less than 1 to the power k, as k tends to infinity, that's going to tend to 0. So what this means is this second term here will totally disappear. That will tend to 0 as k tends to infinity. So we're left with alpha 1 times lambda 1 to the power k times the eigenvector v1. That means, okay, that means the error is dependent upon lambda 1. Okay, lambda 1 is your spectral radius. That's the largest eigenvalue. Your error depends upon that. So the smaller the value of lambda 1, the smaller your error. The smaller your error, the quicker your convergence. So in short, you calculate the iteration matrix for your methods, calculate your spectral radius. The one with the smallest spectral radius will converge the quickest. Okay. Okay, the problem is eigenvectors and eigenvalues can be expensive calculations. Okay, MATLAB has the Eigen function. You can type it in a fraction of a second, it will give you an answer. What if you got tens of thousands of values? What if you got a matrix which is 10,000 by 10,000? That might take a while to calculate your eigenvalues. So this is where we can use a useful little theorem. This is Gauss-Gorin's theorem. Okay, this is a way to estimate the upper bound of an eigenvalue. Okay, so what we have is A is a square matrix, and R is the sum of all absolute values on the non-diagonal elements of the ith row. Okay, so R is essentially you sum the row, but you miss out the diagonal element. All of the eigenvalues are bounded by a circle, which is defined by the center at the diagonal element with the radius of R. Okay, so that's Gauss-Gorin's theorem. So you can calculate what's the upper bound of your eigenvalue by using Gauss-Gorin's theorem. And it also applies for the column sum as well. So strictly speaking, Gauss-Gorin's theorem is stated as a row sum, but it also applies to the column sum. So what you have is here you have a complex plane. Okay, our center is going to be the diagonal element. That's going to be a real number. So our center Aij is here. The radius is the sum of all the absolute values of the non-diagonal elements on that row, okay, or column. Okay, so we know this states that our eigenvalue must lie somewhere within this circle. Okay, so let's have a look at an example. Here we've got a 3 by 3 matrix. I know it's easy to calculate the eigenvalues for this matrix, but I'm just doing it for an example. Okay, well, the radii, okay, what you do is, let's take the 5, for example. So first row, first column, that's our diagonal element. What I do is I calculate the sum of the non-diagonal elements in the row, and I also do the same for the column. Okay, so remember we're taking absolute values here. So absolute value of 2, or minus 2 is 2, plus 1, plus 0. So that gives me the 2 plus 0 there. And in a column, I have 1 plus 0. So that gives me the 1 plus 0 there. And I take the minimum. Okay, so therefore, my first radius will be 1. For R2, I take the second diagonal element, which is minus 3. Okay, row sum will be 1 plus 2. Column sum will be 2 plus 1. Same thing. So I have 3. And the third one, okay, the diagonal element is 2. The row sum will be 0 plus 1, and the column sum will be 0 plus 2, and therefore I have 1. So those are my 3 radiuses, or radii, of those circles. Okay, so for the first circle, I'm going to have centered at 5 with a radius of 1. The second circle is going to be centered at minus 3 with a radius of 3, and the third circle is going to be centered at 2 with a radius of 1. Okay, so the actual eigenvalues, well, lambda 1 was 4.7644. That's within this circle. So if we're only looking at the real numbers, centered at 5, radius of 1, so it can be in the range 4 to 6 along the real number line. So that's within that range. Second circle, centered at minus 3, radius of 3, so that can be anywhere between minus 6 and 0, which is minus 2.25. And the third circle, centered at 2, radius of 1, so anywhere between 1 and 3. So that gives me that eigenvalue. So Gauss-Gaussian's theorem doesn't give you the eigenvalues. What it gives you is what's the upper bound. And that's a useful way of estimating the spectral radius. So if you can't calculate, if you have a determinant, say 10,000 by 10,000, that's going to take you a long time to calculate that determinant. Well, a row sum and column sum is quick. So we can estimate what's the upper bound of our eigenvalues using Gauss-Gaussian's theorem. Okay, here's an example. Use Gauss-Gaussian's theorem to compare the rate of convergence between Jacobi and Gauss-Seidel. Okay, so here we have a linear system which we've been solving. Okay, calculate the iteration matrix for the Jacobi method. Okay, so what you do here is you calculate D, you calculate L, and you calculate U. Okay, remember L and U aren't from LU factorization, they're just simply lower and upper elements with their signs negated. If you do that, you'll get this iteration matrix. Okay, using Gauss-Gaussian's theorem, okay, so we've got a row sum is 2/7 plus 3/7, and column sum is 2/5 plus 1/3. Okay, same for the second one. So we have 2/5 plus 1/5 across the row, and 2/7 plus 1/3 down the column. Okay, so you do that. Okay, so here's your radiuses or radii. Okay, so then you pick the one. Okay, you want the spectral radius. You want the one which gives you the highest. Okay, the worst case scenario. So the one which will give you the highest, well, the centers are all at 0 because the main diagonals are 0. So in other words, we look for the largest radius, which is 0.714. So our eigenvalue can be as much as 0.714. It can't be more than that. So we say, okay, let's say our spectral radius is equal to 0.714. That's for the Jacobi method. What about Gauss-Seidel? Well, if you calculate the Gauss-Seidel iteration matrix, okay, I'm not going to show you the calculations, but that's what you get. Okay, using Gauss-Gaussian's theorem, Okay, I've taken out a factor of 1 over 210 just to make the arithmetic easier. Okay, so for the first one, we have, well, the column sum is just zeros. Row sum is 60 plus 90, which is 150. For the second one, I've got 78 or 88. And for the third one, I've got 28 or 168. Okay, so my three radii are 0, 0.371, and 0.133. So what you do is you determine, okay, which has got the highest bound. So the first one is 0 plus 0, which is kind of useless. The second one is 24 over 210 plus 0.371. And the third one is 56 over 210 plus 0.133. So it turns out that this one's the highest. So it's 0.485. So that gives us our upper bound for our eigenvalue for that TGS, that iteration matrix. Okay, so this is our spectral radius for the Gauss-Seidel method. And from the previous slide, we had a spectral radius of 0.714 for the Jacobi. Therefore, the Gauss-Seidel method should converge faster. And we saw in the first lecture that was the case. It converged within 8 iterations rather than the 14 that the Jacobi method took. So Gauss-Gourin's theorem is useful. For systems which you'll be doing perhaps in, for example, an exam paper, you could probably just use the eigenvalue command in MATLAB. Okay, if you had 1,000 by 1,000 matrix, you'd probably want to use Gauss-Gourin's theorem. Okay, so that's how we analyze the convergence behavior of different methods. Okay, I'm going to finish off by having a look at what we call the successive over relaxation method, or SOR. Okay, this is a method which improves upon Gauss-Seidel. So even though Gauss-Seidel is faster than Jacobi, we can still improve on it. Okay, successive over relaxation basically uses a weighted sum of the values from the Gauss-Seidel method. And it's quite a neat bit of mathematics. Okay, so what I've done here is I've got an equation, a single equation from a linear system. Okay, and what I've done is I've grouped all of those terms to the left of the main diagonal in this summation. Then I've got the main diagonal term, which is in the middle. Then I've got the term to the right. Okay, so in a Gauss-Seidel method, this would be using the current values of x, and this would use the previous values of x. Okay, well, what I'm going to do is instead of A11, or say AII, okay, I'm going to replace it by this weighted sum. Now, I just want you to just take a second just to realize that the left-hand side and the right-hand side are equal. Okay, all I've got is 1 minus 1 over omega times AII plus 1 over omega times AII. If I was to expand this out, the minus 1 over omega and the plus 1 over omega would cancel out, and I'd just be left with AII. Okay, so I haven't changed anything. Okay, this, by introducing omega like this, I haven't changed any of the values. So replacing this right-hand side here in place of AII, I get this. Okay, and I'm going to rearrange that to make xi the subject, and that will give me my SOR method. Okay, bit of algebra here. Okay, subtract the summations from both sides. Okay, it gives me this step. Okay, so all I've done for this step is taken both summations over to the right-hand side. And what I've done here is I've multiplied everything by omega. Okay, so I multiplied everything by omega here. So the 1 becomes omega, 1 over omega just becomes 1. Okay, subtract this term from both sides. Okay, it gives me that. And finally, divide by AII, and we get down to this. Okay. Well, this is going to be my value of the next iteration. Okay, this left-hand side. This xi here is going to be my value from a previous iteration. And this you might recognize as the Gauss-Seidel method. So essentially, we've got something multiplied by the value at the previous iteration plus omega multiplied by the Gauss-Seidel method. So that's what I mean. So that thing in the underbrace, you can see there's an underbrace there. That is all the Gauss-Seidel method. So that's omega times what we call x bar. And x bar is just Gauss-Seidel. Okay, so x bar is the value of x calculated using the Gauss-Seidel method. X to superscript k minus 1 is the previous value. So essentially what we got is 1 minus omega times the previous value of x plus omega multiplied by the Gauss-Seidel method. Okay. So this is a weighted sum. That value of omega will tell us how much of the old values to use compared with how much of the new Gauss-Seidel values to use. Okay. And this omega parameter allows us to tune the method. Okay, so what happens? What are the effects of omega? Well, omega has to exist in the range 0 to 2. Okay, it can't be outside that range, but it can be any number. You pick what number of omega you want. Okay, when omega is in the range 0 to 1, okay, are you familiar with this notation? So the square bracket means including 0. The rounded bracket means not including 1. So this means omega is greater than or equal to 0, but less than 1. So if omega is less than 1, the method applies more weight into the older values and less to the Gauss-Seidel method. This is what we call under-relaxation. If your values of omega are greater than 1, the method applies less weight into the older values, but more weighting to the Gauss-Seidel values. This is called over-relaxation. So you want to use under-relaxation when the Gauss-Seidel method overshoots. Okay, if the Gauss-Seidel method sort of overshoots your solution and it keeps sort of oscillating about the solution, you want to under-relax your method. If it doesn't overshoot and you want to give it a bit of a sort of helping hand, a bit of a bump, we use over-relaxation. Okay, so that value of omega is like tuning. It's like it's going to be different for whatever system you're solving. When omega is equal to 0, the method is simply the Gauss-Seidel method. Okay, so how do you determine what's the best value of omega? Okay. Oh, sorry, before I do that, let's have a look at an example. Okay, this is the same system we've been looking at before, is it? I think so. So I'm going to use Gauss-Seidel and SOR methods to solve this system here. Okay, using a relaxation parameter of 1.25, and I'll explain why I've used 1.25 in a minute. Okay, so here we have 1.25, so this is 1 minus omega multiplied by the previous value of x plus omega over 4 because the coefficient of x1 is 4, and that's just your Gauss-Seidel method. Okay, so for the first one, we only use the previous estimates. For the second one, we use current estimates where our number is less than I. Okay, so that's our SOR iterations. Okay, I've calculated this using MATLAB, done the programming, and this is what we have. If we use Gauss-Seidel method, okay, this is when omega is 1. It takes 24 iterations to obtain a solution where the norm of the residual is less than 10 to the minus 4. Okay, if we're using successive over-relaxation, it takes 10 iterations. Okay, so just to 24 for Gauss-Seidel method, just 10 for SOR method. Much, much quicker. Okay, it's an improvement. It's sort of supercharged Gauss-Seidel method, so to speak. Okay, same solution, by the way. Okay, you should always get the same solution, just the speed of convergence is what's of interest. You know, just flip over that worked example. I don't want to get sort of bogged down with doing calculations. Okay, so let's do some analysis. We've already seen that the iteration matrix, the norm has to be less than 1 for it to converge, and the spectral radius gives us our speed of convergence. Okay, so calculate the iteration matrix for the SOR method using A equals D minus L minus U. Okay, so what we have here is I've introduced a relaxation parameter. So remember, your diagonal elements are your xi's. Okay, so if I just go back a couple of steps to the, okay, so here we had, here, okay, so essentially this term here is related to the diagonal elements. Okay, so that's where this comes in here. So your diagonal elements, okay, so you apply the relaxation parameter. So 1 minus 1 over omega times D plus 1 over omega times D minus L minus U. Okay, that is the same as saying D minus L minus U, but just with that relaxation parameter added. Okay, substitute into the linear system. So you have AX equals B. So instead of A, you have this expression. Okay, and doing a bit of jiggery-pokery. Remember, your diagonal elements and the lower triangular elements can be applied to your current values of X. Okay, your upper diagonal elements can only apply to the previous. Okay, multiply both sides by omega. Okay, so get rid of all the fractions. Okay, take this second term over to the right-hand side, and then we can multiply by the inverse of D minus omega times L. Okay, so this is what we have. Okay, remember this term over here, we get rid of, you know, well, I don't say we get rid of it, but we're not interested in that. We're only interested in the iteration matrix, what is being applied to X. Okay, so our iteration matrix is this coefficient of X. Okay, so in short, the iteration matrix for this SOR method is this expression here. Notice it's in the form of D, L, U, and omega. So the value of omega will determine what the value of TSOR is. Okay, so depending on what your omega is, you'll have a different iteration matrix. So therefore, you'll also have a different convergence. So if we want to find the optimum value of your relaxation parameter, we just pick the value of omega, which gives you the smallest spectral radius. So the spectral radius will depend upon omega. Okay, so what you can do is you can test it for all different values of omega, calculate the spectral radius, whichever gives you the smallest one, that's what you choose. Okay, so for example, this is the system we just solved. Okay, find the optimum value of the relaxation parameter. Okay. Yeah, why not? I was going to say, let's show you how I did. I'm going to show you how I produced this graph here. Okay, so to do so, I'm going to have to switch over to our old friend MATLAB. Oh, tell a lie. Sorry, I won't bother doing that. I just realised I've got it in the notes. Okay, so I should have put this on the slide. Okay, what I was going to do is just type this out, but then I've just noticed I've given it to you in the notes. So what this little piece of code does is, if I enter in the coefficient matrix A, extract D, L, and U. Okay, I've used tri-L and tri-U. They just extract upper triangular and lower triangular matrices. Okay, so this gives me D, L, and U. And I created a vector of omega values. So starting at 0, going up in increments of 0.1, 0.01, up to 2. So I'm going to calculate the spectral radius for all of those values. Okay, so what I do here is I loop through my omega vector, calculate the iteration matrix, so inverse of D minus omega times L, etc., etc., and then calculate what the spectral radius is. So rho of ith value, so that's the ith value within the omega vector, is equal to max absolute eigenvalue of TSOR. And then all I've done there is plotted it. So plot omega against the spectral radius. Okay, and if you do that, you get this graph. So that blue line shows you the spectral radius. The smaller the spectral radius, the quicker convergence. So therefore, around about there is where we want to use as our relaxation parameter. And that's around about 1.25. Okay, that reading off on the horizontal axis, that's about 1.25. That's why I used it in that previous example. Sorry? You do have to use Gauss theorem, yeah. You might not get the absolute optimum, but you'd get optimum what you could, yeah. That's a good point, yeah. So this was a 3x3 system, very easy to calculate eigenvalues. If you had a large system, you'd have to use Gauss theorem. Okay, there's another theorem. If and this is only for a few cases, if you're lucky enough to have a positive definite. Okay, guys. Sorry, a bit of chatter going on. If you're lucky enough to have a positive definite and tri-diagonal coefficient matrix, there is a straightforward formula you can use to calculate in the optimum value of the relaxation parameter. Okay, and it's this. Okay, I've shown you this without proof. Okay, so this uses the spectral radius of the Jacobi method. So this rho Tj is your spectral radius of the Jacobi method. Raise it to the power 2, plug it into this formula. That'll give you the optimum. You might think, hang on, how often are we going to have a positive definite tri-diagonal system? Well, if you use, as we did with boundary value problems, if you use second order finite differences, you end up with a tri-diagonal system which is positive definite. Okay, so quite often for boundary value problems, this is quite useful, especially if you're using finite differences. Well, let's apply this to that example we just looked at. You could use Thomas, yeah. You could, but we don't cover it in this unit. I deliberately haven't mentioned Thomas because it's outside the scope of this unit. It's in the PDE's unit, but not in. Yeah, you could use Thomas, yeah. Okay, so, all right, guys, there's a bit of chatter going on. Okay, it's only a few more minutes, so keep quiet until then, I hope. Okay, so let's have a look at the optimum value of omega. So instead of calculating the spectral radius for all those different values and just picking the smallest one, what we can do here is calculate the iteration matrix, the Jacobi method. Okay, so recall it was inverse D multiplied by L plus U. I should mention at this point, in an exam, I will give you the iteration matrices. Well, I'll give you it in this form. You don't have to remember these. Okay, so calculate the iteration matrix, and we get this down here. Okay, calculate the eigenvalues. Now here I've done it by hand. Don't recommend that, just plug it into MATLAB. If it's small enough system, plug it into MATLAB. If it's too large, use Gauss theorem. Okay, so we have three eigenvalues, 0 and plus or minus root 0.625. So if we square root 0.625, we get 625. Okay, guys. Okay, so if we plug it into that formula, we get 1.24, which is damn close to what I used before, which is 1.25. So you can see that 1.24 corresponds with this point here. Right, so that's what I wanted to cover on indirect methods. I've just got a couple of summary slides just to sort of, we've covered a lot of ground today, especially quite a few bits of analysis. So I just sort of wrap it all together. Indirect methods are iterative methods. They use multiple iterations to refine a solution. These are much more efficient than direct methods for large systems. Okay, direct methods are all right, they got their place, but for practical applications and for large systems, we only use indirect methods. The residual is, okay guys, we have less chatter please. The residual is calculated by B minus A times your estimate of the solution. Okay, and that's used to determine a current estimate of how close we are to our actual solution. The smaller the residual, the better. We cease iterations when the norm of the residual is less than some tolerance. You set that. That's what, the smaller the tolerance, the more accurate your solution, but the more effort you have to do. Indirect methods converge when the iteration matrix or the norm of the iteration matrix is less than 1. Okay, and the rate of convergence is given by the spectral radius of that iteration matrix. So the spectral radius is a maximum absolute eigenvalue. Okay, and of the indirect methods, we looked at the three main ones: Jacobi, Gauss, Seidel, and SOR. Jacobi only uses values from the previous estimate. Gauss, Seidel uses values as and when they're available. SOR method is a weighted sum between the previous estimate and the Gauss-Seidel method. And finally, in the SOR method, to find the optimum value of the relaxation parameter omega, it's the one that gives you the smallest spectral radius of the iteration matrix for the SOR method. Okay, 5 minutes left. Any questions? You sort of look quite stunned. Okay, I know you did use these things last year, but this year we're looking at them more from an analysis point of view with regards to spectral radius and things like that. Okay, right, so this week in the tutorials, have a go at the tutorial exercises. Before you come to the tutorials, I know the ones who's got it in the next hour, that's not possible. And next week, we'll be looking at QR factorization. 1 minute to midnight. But I wouldn't recommend, please